Hey guys, Miss McMahon here. We're going to go over some exponential questions, and I'm going to do my best to clarify every step of the way how we get to the correct answer. So the first one we're going to look at is 6x to the 10th times 12x squared. And if we're multiplying this, then I can just write it a little more cohesively. And what we have here are four different things that are being multiplied together. And we can multiply things in any order. We know that 3 times 5 equals 15, and 5 times 3 equals that same 15. So that helps us see that we can multiply things together in any order. So if we can do that, I'm just going to start by rewriting some of the more common things that we need to multiply. And so we could go ahead and start by saying 6 times 12 is 72. Because that might be a little bit easier for some of us. And then to multiply the x's together, we're going to actually break it apart and expand it a little bit first, because that's my favorite thing to do to really see what's happening here. So we have x to the 10th, which is x multiplied by itself 10 times. So that would be x times itself 10 times.
3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9,
10. Okay. X times itself 10 times. And then we have multiplied another x squared. That's x times itself 2 more times. So we're going to multiply by x 2 more times. X being multiplied by itself 12 times. So that can be shortened into x to the 12th power, because that's 12x is being multiplied by itself. So when we take 6x to the 10th times 12x to the second power, or 12x squared, that simplifies to be 72x to the 12th. All right, the next problem we're going to talk about is how to simplify 2x squared plus 2x. And this is already simplified. It cannot be simplified anymore because x squared and x to the first power, which this is to the first power, we just didn't write it because we don't have to write a first power, are not like terms. They cannot be added. This would be kind of like asking, how do you add a whiteboard marker and a pen? And you could say, well, if I have the two of these, I have 2 writing utensils, but I can't say that I have 2 pens, because I don't. I have 1 pen and I have 1 whiteboard marker. And so that is kind of one way to think about how these are not like terms and they cannot actually be combined. I can't take this pen and morph it into a whiteboard marker. So we could factor a 2 out and get x squared plus x, and then we could factor an x out and get x plus 1 if factoring is what you're after, and that's considered more simplified. But ultimately, these 2 terms are not like terms, and they cannot be added any more than they already are. The only way we could proceed more with this expression is if we were given some value of x and we were able to plug it in and evaluate this expression for that value of x. But ultimately, can't add these. They're not like terms. I cannot say right now that I have 2 whiteboard markers because what I have in my hand is 1 whiteboard marker and 1 pen. The only thing I can say is that I have 2 writing utensils. All right. Now, I think every math teacher on the face of the earth has probably seen these two expressions written as equal to each other. The question is this true or false? It is absolutely false. These two are not equal to each other. And I'm going to show you why. And I'm going to use the area model to show you why. I'm a big fan of the area model because it does a great job of showing why things work, as well as laying out our work in a manageable way. So first of all, a plus b quantity squared is the same as a plus b times a plus b, because squaring something means you take that thing and you multiply it by itself twice. So that's how we're taking a plus b and we're multiplying it by itself twice. And then I'm going to think about this is the base of my rectangle and this is the height of my rectangle. Although in this case, this rectangle would actually be a square because the base and the height are the same thing. So I'm going to lay out my square. And along the base, I'm going to have a plus b. And along the height, I'm going to have a plus b. And to find the area of a square, we take the base and the height and we multiply them. And what we actually have within this square is four smaller rectangles. And so I'm going to find the area of each four of these individually. So for the first one, we have a times a as your base times height is a squared. And then for this top right one, we have base times height is b times a, or a times b. Doesn't matter, you can multiply in any order. So that's the area of that little rectangle with a base of b and a height of a. Down here we have a base of a and a height of b, and so that is again going to be a times b, since the area of a rectangle is base times height. And then down here in the bottom right, we have a base of b and a height of b. So when we multiply those two together to get the area, we're going to get an area of b squared. And so that means that a plus b quantity squared is equal to all of these four areas added together. And so that would be a squared plus a times b plus another a times b, so that's one of those plus another one of those, which is going to be 2ab's plus b squared. So when we take a plus b quantity squared and we multiply it out using the area model of the whole base times the whole height, gets us all four of these little mini areas. We get a squared plus 2ab plus b squared. And so you can see that that is not equal to a squared plus b squared. What is missing from this expression to make them equal is this middle term of plus 2ab. So someone thought that you could distribute a square across addition. You cannot distribute a square across addition or subtraction. You must multiply it out so that you're in compliance with order of operations, and that gets you a squared plus 2ab plus b squared. All right, so the next problem we're going to look at today is, does y cubed squared equal y to the 6th or y to the 5th? And we're going to investigate this by expanding this term right here, because that is my favorite way to look at exponential expressions, and break them down and simplify them. So starting with the outermost layer, we know that when we square something, that means we are multiplying it by itself twice. So I'm going to take the term and rewrite it as y cubed times y cubed, because that is y cubed multiplied by itself twice. And then when we cube something, we know that that means that it's multiplied by itself 3 times. And so I'm going to rewrite each one of these to be multiplied by itself 3 times. And what I want you to notice here is that within the parentheses, everything is being multiplied, and outside of the parentheses, everything is being multiplied because that's what the parentheses mean. So ultimately, through this whole expression, we have y multiplied by itself 6 times, which is why the expression is equal to y to the 6th. All right, the last rule that we're going to take a look at today is why does this equal this? Why is it that when you take the same base raised to two different exponents and divide them, why does that turn into subtraction for the exponents? And we don't really want to just say, oh, well, that's the rule. We want to know why the rule works, because it wasn't like someone just decided, oh, it's just this is going to be the rule. It's that this became the rule because it worked, because it was a consistent pattern that was proven to be true. So we'll take a look at, say we have x to the 5th divided by x squared. We know that x to the 5th means that x is going to be multiplied by itself 5 times. So there we have x multiplied by itself 1, 2, 3, 4, 5 times. And then we know that x squared is x multiplied by itself twice. And so what happens that again makes this rule true is that we have an x divided by an x, and anytime we have anything divided by itself, it cancels out to be 1. And multiplying by 1, we know doesn't change a number, so that's just going to sort of disappear into invisible math because we don't bother to write when we multiply by the number 1. And then we're going to have another one of those. We're going to have another x divided by x cancels out to be 1. And so that's going to leave us with x times x times x in the numerator divided by 1, which is just itself. So this is x times itself 3 times, which is x cubed. Divided by 1, again, is just itself, so we could just leave it as x cubed. And what I hope you notice is that that is the same as x to the 5th minus the 2nd power, because 5 minus 2 is going to give us an exponent of 3. So again, it's not just that someone decided that this rule was going to be the end-all be-all of dividing exponents of the same base. It's that it worked mathematically. We had the cancellations that resulted in the same thing as subtracting those exponents. So I would say, again, that if you're ever unsure about how to handle an exponent expression like this one right here, that you expand it, that you make it as big as you possibly can so that you can actually see how things are going to multiply out, see how things are going to cancel out, and do the simplification by hand so that you can be confident and know how and why it worked out that way, that you can do each step sort of individually and see what's left over. So I hope that was helpful to you. Please reach out with any questions. I would be happy to throw in more support as I can. Hope you have a good one. Thanks. Bye.